Okay, YouTubers, this is Advanced Tech Engineering again, and what I'm going to be showing you today is an experiment, and what this experiment is going to compose of is I'm going to use this little brick cell that you see here, and it is old, just a crappy brick cell, and what we're going to do with it though is going to be interesting. I'm going to show you what you can do by using our electronics, which are not yet available on the website yet. They will be soon, and what we're going to do is demonstrate that at least with our chemistry, and we realize we use a different chemistry than everyone else, that the maximum number of plates you need in a 12-volt cell is 6 plates. Okay, so let me go over this setup just a little. So, I mean, it's pretty basic, but let me explain it. So over there, we got our reservoir, and we have an in and an out there. The bottom one is the out. It's going to go through that pump. There's a drain over there, so I can get rid of this chemical whenever I want easily. Comes out of the pump, goes through the bottom of the cell, and goes through the cell, out the other side, back into the reservoir, and we have an output for hydroxy, which is there, and then we have the bubbler, which we're not going to use. We actually just have the flow meter attached to the bubbler so that you can see the flow, and this bubbler is holding it up so I don't have to hold on to it. So anyway, we're not using the bubbler, we're just using the flow meter. And what we're going to show is, so first we're going to hook this thing up. We're only using 6 of these plates, so I'm going to show you those connections. We're connected here, which this rod goes through here. It is not touching this plate. It simply, let me see if I can get a good angle on that, simply just goes through the hole, and it does not touch it. Okay, so what we're attached to is right here. Okay, and in between this plate that my finger's on here and this acrylic here is 6 plates. The other side, spin this around so you can look at it. We're attached here. We got our negative terminal, and yeah, it's a long bolt. We're going to use that bolt to go through later on though. So we're attached right there to this plate, which is up against the acrylic. So there is only 6 plates between this plate and the one on the other side. Okay, there's a lot of plates in this cell, but we're going to use those later on. Not all of them, but we'll use more. Okay, so I don't know if you can see the number of plates there. You could pause it and you could count, and you could see there is only 6 plates. It's very important that you understand that, and that I know there's a lot of skeptics out there, but you can see we're not connected there. And yes, I could put an ohm meter on this plate and put it to this bolt so you could see that, but it would represent an invalid value because of the chemical in here is conductive, which would show something on this plate. Okay, so not going to do that. So how we are connected, we got our 2 positive negative wires here. They come over to our badass power supply and they're connected to our 12-volt section. Okay, it's not on. Also, we have these alligator clips here which are connected. I just have them clamped to here, and these littler alligator clips are running over to the pump. Okay, so we're running our pump and everything off that same output on the power supply. And a thing to note, the reason I have my clamp meter here is because I'm going to show you the current on this negative wire, and I will show you the total current over here, which is going to be different because of the pump draws about 7.5 to 8 amps. So this is going to be off a little bit, and I know there's a lot of skeptics out there, so I have to show the difference. And okay, on this we're just connected to the back of the flow meter in the bottom. It's real simple, and it's gonna show, I don't know, 4.5 liters a minute. So let's go ahead and give this a shot. Now, actually, before I go ahead and turn it on, let me go over this purpose. What I'm going to show you is how when you parallel these 6 cells with the next 6 cells, that it makes no difference. Okay, and then I'm going to show you, but using our electronics, how you can make it work, how you think it should work. I'm also at the end going to go over this using a drawing electrically, how people think of these and how it actually is, and I'll show you how we think about them electronically, like if you had an electronics degree, an engineering degree like me, or if you just have an associate's degree or any, you know, self-taught electronics background, you might look at this similar to how we do, or electrical engineers look at them, and I will show you that. Okay, so let me go turn on the power and I'll show you. It's going to draw quite a bit of current, and my camera's plugged in. I'm currently snagged on something. Okay, so here we go. We got the power on. Look at that. So you can do the math yourself. You can see the power consumption right there. Now we're going to come over here. I'm going to hook this clamp meter around here so you can see the difference. Whoop, it's getting away from me. There's your difference. Okay. Now we're going to come over here and look at the flow meter. And let's see if I can get eye level with that. You can see what we're drawing there. We're just drawing approximately 4.5 liters a minute. Okay, so you got to remember this. I'm gonna shut the camera off here for a second, and we'll hook this up differently, and we'll be right back. And I'm gonna turn this power supply off. So, well, let me turn it back on one more time so you can see it does. You know how it drifts. So that's the total current and the voltage. The voltage is about 12.5 actually. I measured it with a fluke meter just to see. And then over here, that's what we got. Okay? So I'm going to shut this off and I'll be right back with the next setup. And we're back. So, okay, so now what we got, our setup. Now, everything's the same except for I changed the electrical connection. So we're the same on this side. We're still tapped here. We're not connected through there at all. We're not touching. It's not touching there. Okay. So now what we got? Same thing, right? 6 plates in between this plate and the acrylic on this side. Other side, however, has changed. So let's look at that just so you can see. Okay, now we are tapped onto this plate and this plate. Okay, so we got what, 12 plates or so in there. There's 6 plates. Okay, so there's this plate now is using the other side of what we saw over here, this plate, as its center tap for its 6 volts, or its 12 volts, sorry. So we'll get 12 volts between here and here, and 12 volts or 12.5, whatever we got on the power supply, from here to the one that's touching, to the plate that's touching this acrylic. Okay, so that would be this plate right here. So we're paralleled just like everybody does, right? Normally they'd run this bolt clean through and they'd tag it onto there, and it'd be every other one over there. Okay, this isn't anything new. I'm just making sure you understand what we're doing here. So now we're hooked up, so we got an additional 6 plates in there with 12 volts across them. Alright, so now what we're going to do is we're going to turn the power back on, and you will see what happens here. Let me hook the clamp meter back up over here, and we will look at our flow, we'll look at our power. You can compare it from earlier in the video, and here we go. Okay, there's our power. Now remember, the amp meter is showing approximately 7 to 8 amps high here. And these clamp meters are not as accurate as an inline meter, but there's the difference. So now let's go over to our supply, or our output. You can see that we're still at approximately, let me tilt this up, 4.5 liters to a minute. No difference, right? Surprised. So I added 6 plates, and what did we gain? We gained however much 6 plates cost is what we've gained, right? We didn't gain anything. So there you go. Again, power consumption. You can do your own math. And power consumption just at the cell. Okay, that's what we got. I'm going to turn the power supply off. And now what we're going to do is we're going to hook it up the Advanced Tech way, okay? Now we're going to probably double the output here, and when you double the output you will double the power consumption, okay? So it comes with a cost. However, this is good for taking a small cell and make it into a big cell, because now with these electronics what you can do is you can take cells and actually add them together, and they will do what you think they should do, which is, why can't I double my output by adding another section of cells? Okay, and I will explain why you can't do that in very basic terms, okay? So I'm gonna disappear, we're gonna hook up the next experiment, and I'll be gone for a split second, and we'll be right back, okay? Okay, we're back again. For you it's been less than a second. For me it's been a week or so. So I'm trying to remember exactly where we left off, but a few things I need to mention now that it's been that while for me is this chemistry has been sitting around for that long, and it does degrade over time. So it'll probably draw a little less current than it did before, and maybe a little less output than we had before, although it's mostly the same. I mean, it's not going to be that big of a drop. So what I'm going to do now is go over our new connections from what we had before. So now we've got our positive and negative here. This hose is kind of in the way, but it's over there. It's the positive, and we are connected right here on the negative terminal. We're not touching this plate here. It just goes through the hole, doesn't touch. I'm not using most of these plates on this side, but anyway, we got a connection there for this negative. We got a connection here for this negative, because this one is also negative. Okay, so let me show you the other side. I'm going to do an over the top view here just to kind of get an idea, so you can kind of follow both these plates actually. So the two negatives are over here. On the other side we got one here, if I believe I'm right, and that were attached on the positive side over here, and then we're attached to the positive side against the acrylic on this one. So now let me flip that around so you can see it. Okay, so there's our positive coming through. It goes through that plate. Yeah, okay, and is touching this plate. So we're not touching here. We're just touching here. So we got a positive plate there, and our other positive here. So it's kind of hard for me to explain this a little. Well, it's not difficult, but anyway. So what we have, okay, there's a positive plate, and its associated negative, which is over on the other side of this, is right here. So you can see they're offset. Maybe you can see that, I don't know. This plate to this plate, there's 6 plates in between there, okay? Let me see if I can get an angle where you can look down and see that this plate here is offset, you know, and there's 6 plates between it on the one that's just right down there. So it's hard to get a good camera angle with all this to explain it properly, so I hope I can do an okay job, but if you were here it'd be a little different. So there's 6 plates between these two. Basically we have our electronics that is electronically separating the 2 sets of plates that we're going to be using. So now on the other side, for the other 6 plates, we got this plate in the middle, which is the one we've been using, and then the one that's over here against the acrylic. Sorry, and those are our other 6 plates. So, see, right here. So between here and here, 6 plates. And then next one we go, we're actually skipping some plates, is why it looks funny probably, because there's another 6 plates here, but we're actually using the plates that are on the opposite side. So this plate this way, 6 plates, which ends us up on this one across. So I don't know if you can see the offset from that over to the other side. Let's see, it's kind of hard to tell on this little tiny screen on the camera, but we are now using a little differently than we did before. We were using 12 plates, but we are basically forcing the current to go the way we want it to go. So this cell, when paralleled to another cell, and when I say cell, I'm talking about a set of 6 plates. When you add 6 plates or parallel 6 plates with another 6 plates, that it is actually paralleling them. And I'll show you what I mean in the drawing that I mentioned I'm going to do later, to show you what you think it is supposed to do as opposed to what's going on. Okay, so we're still connected to the power supply with both of these connections, and I've got this power supply wired up internally to do what I want it to do, and that's why the lid is off now. It wasn't before. And I've got another set of wires coming out of it so that I can do what I want to do. And our other set of wires are just these 2 new ones, and the other 2 are still the same place they were before, and we're not turned on at all. And we got our pump set up the same way. You can see I moved these a little bit. And then I'm going to show you with this setup. Now you don't exactly double your output, you'll see. However, to see exactly what you're flowing, you would need a very high precision meter to see that, and it would be a digital meter, which is expensive, so we don't use that. So in reality here it might say we're getting 4.5 the way we had it before, and now my guess is would be somewhere around 6. So there is some I can tell there's a discrepancy in the meter. And actually, if I did this with well, I don't even think that would work. I was going to say use one of those bubbling type meters where you just put it in the water and let it fill up like most people do, which they're both probably just as accurate. But anyway, this is what we got. So what's going to happen, I'm going to show you the current on the other side, the other power supply with this clamp meter, because I don't have any other way to show you. The voltage is going to be the same on these 2 as it is on these 2. And again, I will show you what the pump is drawing to, because I watched those other videos and I want to clarify. It shows that the pump's maybe drawing 5 amps, but in reality, this, like I said, the clamp meters are not as accurate as the inline meters. So again, you'll see a high current on here as well as on here, and they'll be close to the same, you know. And unlike before, when you saw, it was the same when we did it the traditional way, in which is the way everyone else uses. This way, you're going to see this one will draw, I don't know, roughly 60 amps, and this will draw roughly 60 amps. So you are doubling. You will know you're doubling your output, and then you're going to see on the flow meter that as well. So here we go. I hope I didn't skip anything over there. And oh yeah, by the way, this power supply, when you're drawing that much power, my circuit breaker is 20 amps, so it's real close to blowing the breaker. So hopefully that doesn't happen. I wish I had a more capacity on that, but we don't. So I will go over this kind of quickly once I turn the power supply on, so that we can get through it and look at all the information just in case that should happen. Okay, so here we go. We're going to turn this on. There's that's 12.8. I adjust the voltage a little bit because I've been using this power supply for other things as well. And there's the power consumption there. Now attach the clamp meter, and there's the power consumption for the other side of the cell. Here is the power consumption, or the amperage that we're drawing on the pump, just so you can all do your math. You do your own math. Now you can see the meter. You get right under there, so you can kind of see, what are we at? Roughly 6. You know, I rate these cells at about 3.5. So 6. This will probably go up to 6.5. And you can see we're doing this with just 12 plates. However, we're using our electronics more wisely, and it's operating like you would imagine it would operate by adding more cells. So now I'm going to turn this off. You can see the power consumption there, so that I don't blow the breaker. And now you can see when you control the current, you can make it do what you want, or make it act how you think it should act and how everybody else imagines this thing acts. Now I hope I'm not leaving out stuff, which I imagine I am, because I've been doing this for a long time, and when it becomes common sense, you talk like everybody knows what you're talking about, but I'm trying not to. So what do we have here? So I'm going to draw these plates. Okay, so here's a polarity fixed plate, and these are neutrals. And I'm not going to draw all the plates, I'm just going to give you an example. Here's another cell, and polarity fixed plate, meaning they're connected to either negative or positive, but they're fixed, where these plates are not fixed. Okay, so what do we have? Let's say we have positive over here, we have negative over here. This is how people connect them. You parallel two cells together like that, and you may have, I don't know what it is, 12 volts going to this. Okay, and you would expect by adding this cell that whatever your power was here, it would double, so times 2. Why? Because you added this cell, and you know, if this one's drawing, let's say 30 amps, and you add another one, it should draw 30 amps too, right? And then you should actually double your hydroxy output as well, right? Well, no, that's not how it works, and I need something so I can erase it. So what actually happens here, I'm gonna just get rid of this a little, get rid of that a little, and we're gonna see what actually happens. So in an earlier video with our larger cell that we actually run the Geo on, runs off at 220, I mentioned that the plates, the maximum size of plates you need to use is 8 inches, and that's 8-inch surface area exposed to your chemistry. So that's roughly a 9-inch plate with a 1/2-inch gasket. So if you go any larger than that, it doesn't matter. If you go smaller than that, however, it does matter. You will drop in current, which is okay if you were putting it in a smaller car. As you could see, we were drawing a lot of power, and in a smaller car you'd want to use a smaller plate to control your current, not pulse width modulation. Okay, so what you're actually doing here is you got your 2 cells, and you add them together by tying these these two wires together and these two wires together, all you're doing is this. You've just done that, okay? What does this mean? What does that mean that I'm drawing these lines? Well, you doubled your surface area. So you increased your surface area by double. And increasing surface area does not necessarily mean you're going to double your output, unless these cells were like 4-inch squares and then you added another 4 inches, you know, until you maxed out your current where it plateaus. You know, it's going to go up and then just plateau once you get to a certain amount of surface area. Okay, that's one of the biggest questions people have about these is, well, how big should I make my plates? Well, no bigger than a 9-inch square with a 1/2-inch gasket, or however you want to look at it, however you build your stuff. Okay, so doing this does not double your output, does not, well, let me tell you what this does do. It increases the longevity of your plates. Why? Because now you've spread out the current over more surface area, you know, so now your plates will last longer. That's the only thing this is really going to do for you. Okay, so let's look at this in electronics type of a view, kind of. So what people think they have, we're going to draw a resistor. My poor excuse for a resistor. Okay, we got two resistors. This is cell 1. This is cell 2, because that's all they are to me. And at an engineering standpoint, is I got two really small resistors. Okay, and I hook my positive and my negative here. Well, in the electronics world, if I hook these two together like this, and I got my leads there, now I've just doubled my current. So now my power is times 2 if these are the same value, and you've increased your current carrying capacity by 2. You know, so whatever it was, you know, times, you know, well, if they're the same value, that is, then you've doubled it. Okay, so this is not how these cells react. You know, you can't just add another one and then get more and more hydroxy out. It'd be nice if it worked that way, but it doesn't. So all you do in the hydroxy world is increase your surface area. You do not change your resistance if you're using the size of plates we use. Okay, so it does not work this way. So I hope that you can understand that. This is a very, very simplistic way of looking at what people think they have versus what is actually happening. And you need some electronics to get this to act the way that you think it should act. And then, yes, you're going to double the amount of current you draw, and you're going to increase your output significantly. And it's not exactly double on the output. This is approximately 260 watts per liter per minute output when you hook the cell up like that, which you can get a little more efficient. You can get down to 200 watts is about what I see normally, and I've had it down to 140 watts per liter per minute, and that's most efficient I've ever gotten it. But now we use this brick cell to demonstrate that you can use these electronics with any cell, because this cell, let's face it, is a very poorly built even cell, but it works, and you could see how much I could get out of it. Now there's a lot of plates in here, I don't remember how many there are, but we could continue to draw more and more and more power and increase the output as high as I wanted to, so long as you have the capacity to draw that much power and not blow your breaker. Now this kind of stuff works great for, you know, if you change your voltage like I do. I prefer to use 220 and 110, but I don't usually see people doing that unless they build in welders or something. But if you're going to run a car, you have to use 220 or higher. And it's easy, you can increase the voltage and then just add plates to adjust to your voltage, because you just need basically half as many plates as you have voltage, and you're good to go. That's the main rule of thumb when it comes to this. Now our chemistry is very unique, I guess. We spent a lot of time developing it. We've been gone out of at least the YouTube world for quite a while, and people probably been wondering what we're up to. Well, we've been doing a lot of development and research and development just to figure out what works and what doesn't work, why things work the way they do, and having a plating background helped out a lot. So we have our chemistry that we make, and we are going to put that chemistry for sale on the website. I was talked into doing that, so we'll do that, I guess. It's not expensive. Might be a little bit more than you're paying now for whatever you use. Potassium hydroxide is a common thing people use. We used to use it. So we'll put that on our website, and along with instructions on how to use it. And these electronics are going to be available after a little more testing. We want to be sure we have it down before we sell to anyone. We don't guess. That's our biggest thing, is we just don't guess. So you can build one of these things to store hydroxy so that you can drive your car on it. In my opinion, it's better than an electric car, because you don't have batteries that are going to go bad eventually and cost you thousands of dollars. I mean, the plates eventually, yeah, they go, but not as expensive as a battery pack, especially if you want to go a long ways. Most electric cars I see people build in their garages will only go like 60 to 30 miles, which is crap. Or you could buy a Tesla, which would go like 200 and some odd miles, but then when that battery pack goes, well, you have to be rich to afford that car anyway. But anyway, we would really appreciate it if we need help still. I know it looks like we're well funded, but we're not. It took us a long time to get this point and develop these new cells. And on our investors relations page, there's actually a donate button. We'd appreciate your help. It helps us further our research faster, and we still work on it regardless. But it's not cheap. We have our new style bubbler again here that is much better than our old one. The other one to me was not pretty. This one we designed, and we build these, and they come in a variety of sizes. This bar here is simply just to hold the meter up. It doesn't actually go there, but you can mount it however you want to mount it, and it's not real expensive. We could make them cheaper if we use opaque PVC, but people like to see inside there, so do we. Also on these bubblers, they come with a check valve. Goes on the input side to the bubbler. When these cells usually heat up, and when they cool down, they have of course a vacuum, and you'll pull your liquid out of here and back into your chemical, which you don't want to dilute and change your output on your hydroxy cell if you do that. So they do come with it doesn't say it on the website, but they do. They come with a check valve. Looks like this. It's just a PVC check valve with a stainless steel valve. So anyway, I hope I went over everything. I tend to forget things as I go along here, and the chemistry is important. Controlling the current, meaning not limiting it, but making it go in the directions you want it to go, is important. Hopefully the electronics for for this process won't be too expensive. That's currently what we're doing now, and why it's not out yet is because we're trying to make everything affordable. And if you can use that electronics on your cell, most people like to build their own cells, then that'd be great, because it doesn't add a whole lot of cost to your stuff. And if you want to try out our chemistry, it doesn't cost a whole lot either, and it comes with instructions, but it works really well. It's the best I've seen yet, and it's not harsh on your hands like KOH. Well, let me take that back. It is harsh on your hands, but unlike KOH, it won't burn you when you get it on you and try to rinse it off. So it does not have an exothermic reaction when you mix it with water, is what I'm saying. So anyway, power supplies, we can build these in any size. We can custom build anything. If you want a smaller version of this with just one output to test in your garage, say you don't need, you know, a 110 and a 220 and a 24 volt, you just want your 12 volt out and you want to be able to draw a lot of current, we can build that for you too. But I gotta warn you, the most expensive thing about these two lower voltages outputs is the transformer. Okay, to be able to handle that much current, you have to have a transformer that will do it. And the transformer alone in this thing is it's just over, I don't know, $400 just for the transformer. So if you want a custom power supply, we'd be happy to build anything. We're an engineering firm is what we really are. We don't just specialize in hydroxy. We actually designed and built a fuel additive system for another fuel additive company that, you know, so anyway, enough from me. Please visit our website, try our chemistry. Please help us out on the donate page. Any amount helps. We appreciate our viewers, and if you have questions, just ask.